Hi everyone. We're going to wrap up chapter 8 with a discussion about energy that accompanies chemical reaction. If you remember, we had discussed that chemical reactions can either release or absorb heat, and when they release heat, we call them exothermic reaction, and when they absorb heat, we call them endothermic reaction. The way we measure the amount of heat that a chemical reaction absorbs or releases is using a term called enthalpy, which has the symbol delta H of reaction. If a reaction releases heat, then its enthalpy change is going to be negative because with respect to the reaction, heat is released to the outside. If the reaction absorbs heat, then its enthalpy change is going to be positive because heat is going into the reaction. So your enthalpy sign would be plus. So the amount of heat emitted or absorbed depends on how much reactants you actually use in the reaction. Here's an example. This is a combustion reaction of methane with excess oxygen. Next to the reaction, we have the enthalpy change given as negative 802.3 kilojoules, kilojoules here being the units of energy. So what this tells you is that the reaction releases 802.3 kilojoules of heat. Now, that quantity depends on how much reactant you're using. In this case, when it says 802.3 kilojoules, it's referring to the fact that if that reaction proceeds according to this equation, meaning that in that reaction, we have 1 mole of methane, so that's the amount of heat you will get if you were to react 1 mole of methane. Similarly, in the product, we have 1 mole of CO2. So that's the amount of energy you will get if 1 mole of CO2 is produced. And lastly, since the coefficient for water is 2 moles, this is the amount of energy you'll get if 2 moles of water is produced. So you can see that these are the coefficients, and that's the energy that you will get. If you use more material, as you might expect, you're going to get more energy out of it. So if I double the quantity of methane from 1 to 2 moles, I will also double the amount of energy that I would release. In the case of 2 moles, then it would just be 1,604.6 kilojoules. So it's exactly twice that number. If I go half the amount of reactant, then I would end up generating only half the amount of heat compared to the 1 mole of reactant. So it's only going to be 401.2 kilojoules of heat. What happens if you have a limiting reactant? Well, the amount of limiting reactant will determine how much energy would accompany that reaction. Okay, let's take a look at an example of how to calculate the amount of energy released or absorbed by a chemical reaction. We're going to look at an example of a combustion reaction that's shown here, where C3H6O reacts with oxygen to produce carbon dioxide and H2O. The original reaction as written releases 1,790 kilojoules of energy. I know it releases because it has a negative sign in front of the delta H symbol, which means energy is leaving the reaction. So let's take a look at the first question. If a bottle of nail polish remover, it contains 155 grams of acetone, that's the first reactant here, how much heat is released by its complete combustion? Again, to calculate this, what you need to think about is that the chemical equation that you have is a mole-to-mole relationship. In this case, the energy is just another component in your reaction. There is negative 1790 kilojoules energy that's released for every 1 mole of acetone. So once you have that conversion factor, to calculate the energy is fairly straightforward. All you need to do is take the acetone that you have and first convert it to the number of moles, which is 58.08 grams per mole. Once you do that, now you have the moles of acetone. You're just going to multiply that by your conversion factor between acetone and energy or heat, and you end up getting negative 4,777 kilojoule. Now, just to be clear, the negative here indicates that heat is released. So in certain cases, if you already said the word release here, you can also not put the negative in there. If your answer is in the form of the delta H, then you would say the delta H is negative 4777 kilojoules. I'm going to do another example. that shows the case when we have two different reactants. So that's part C, where it says if 98 grams of acetone and 103 grams of oxygen is released, if 98 grams of acetone and 103 grams of oxygen are combusted together, how much heat is released? So if we have two different reactants, then we first have to find our limiting reactant. And you can find the limiting reactant same exact way when you did the limiting reactant calculation for products. In this case, you're going to find the theoretical yield, but the theoretical yield you'll find is the theoretical yield of energy. So all you need to do is consider heat produced if all acetone is used up. And to do that, I would take my 98 grams of acetone divided by its molar mass, and I can then express the energy, which is negative 1790 kilojoules per mole of acetone. Now again, why is it per 1 mole? Because in the original equation, the coefficient of acetone is 1. When I make this calculation, I get negative 3020 kilojoules. And again, I really want to underline this idea that the negative here is not a mathematical negative. The negative here means that heat is released. So the actual quantity of energy that is released is 3020 kilojoules. The second calculation you should do is to calculate the heat produced if all oxygen is used up. And to do that, you would take the oxygen, which is 103 grams, divided by the molar mass of oxygen to convert it to moles, and then you would multiply it by negative 1790 kilojoules, because that's the amount of energy you would get from running the reaction. But in this case, with respect to oxygen, and in oxygen's case, you need to use 4 moles of it. So I'm going to put 4 moles of oxygen here. When I do that, I end up getting negative 1440 kilojoules. Again, you can ignore the negative in terms of comparison of the number, but you can see that 1440 is a smaller number compared to 3020. As a result, in this particular context, oxygen is your limiting reactant, and so the amount of energy or heat you will get is 1440 kilojoules.